If you've been following my videos about how to find areas of plane figures, you realise we've finally come to finding areas underneath curves. And this particular lesson is about Simpsons Rule. It's named after Thomas Simpson, an English mathematician from the mid-1700s who has his name attributed to this. It did exist before him. 100 years or so before him, Johannes Kepler was using basically the same rule. I understand from Wikipedia that in Germany it's known as Kepler's barrel rule. But there were others who used it as well. But Simpson's particularly had his name attached to it. It's a common one to learn in Australian schools, and I would presume from what I've seen on the internet in schools in the United States and certainly other English-speaking countries as well. It's a method of finding this approximation of an area under a curve. Basically what Simpson did was he worked out, if you chose the 3 points at the top of each of these columns or ordinates, he calculated what parabola would pass through these 3 points and assumed that the parabola would make a fairly close approximation to the curve, and calculated the area under the parabola. And he came up with this formula that the area would be approximately, now if this point is A and this is B, the point halfway between them is going to be A plus B on 2, that is the average or the midpoint. And the ordinates, this will be the function value of A, this will be the function value of the average point, A plus B on 2, and this height, this ordinate here, will be the function value of B. And he worked this out, that the area will be approximately B minus A on 6 times, actually I really should use a brace here, a bracket here rather, function value at A plus 4 times the function value in the middle, A plus B on 2, and the function value at the end. Now this form of Simpson's rule uses function notation. I'll show you later a form that uses Y notation. I'll show you an even simpler form later. But this is a little confusing. When I was at school, I had 2 textbooks. One of them had a 6 here, and one of them had a 3 with something different written here, and I'll talk about that later. For a little while that confused me, why the 2, but I hope this will become crystal clear for you, just in case your textbook has a 3 as well. Here's my explanation of it. Remember that the trapezoidal rule is finding an average height for a trapezium. That is, if this is length 1 and this is length 2, then the average length of the trapezium will be L1 plus L2 divided by 2. And if the breadth of the trapezium is B, then we multiply by breadth. So we have the average length times the breadth. Average length times breadth, average length times breadth. That's the way we find the area of a trapezium. I want to ask you a question. What would happen if we had another value in the middle? I'll put a question mark here for the moment. We have the same breadth, but how could I find the average of 3 values? Let's call them L1, L2 and L3. I think you would agree that, I'll just rub these out, that you could write L1 plus L2 plus L3. And what would you have to divide by to make an average of 3 numbers? I think you'd agree. You divide by 3. You know that if you're in a class of 3 and you want to find the average mark, you'll add everyone's marks together and share them equally among the 3 of you. Divide by 3. This is exactly the average length. What if I had 4 lengths that I wanted to average? Let's say it's still the same breadth, but I just want an average length of L1, L2, L3 and L4. Well, the area in this case would be L1 plus L2 plus L3 plus L4 divided by 4. I'm wanting you to understand that we can extend the idea of having an average length for a shape times its breadth or width. I want you to have another look at this. Here we have one length here, let's call it, it's the function value at A. We have another length here in the middle, that's the function value at A plus B on 2. That's that function value. And we have a function value here, function value at B. We have 3 lengths. The width is B minus A. There's our width. Corresponds to our breadth here. I want us to move the 6 underneath here and ask the question, how many lengths do we have to average? We have 1 on the left, we have 1 on the right, and we have 4 lengths in the middle. Now they happen to be the same length, but there are 4 of them. Can you see that you have 6 lengths divided by 6? Now it happens to be fortuitous or strange that we often have the divide by 6 here. I've even seen textbooks with 1/6 written out the front. And you'll understand now that I like to have the 6 under here, because I think of the area as a width or a breadth times the average length, or average length times breadth. Does that make sense? The reason there's a 4 here is that it's got to do with there being a parabola, and it just turns out that this middle value is 4 times as important as either of these side values for approximating the area. Now, if you understand that, you can actually have some fun. In my classes, I used to describe this. We'd sometimes use function notation, y notation. So instead of function, we'd have y naught plus y, 4 lots of y1 plus y2 over 6. So that's easier sometimes to write than the function notation. So we've got our 3 y values. And the width we can call b minus a, or we can even call it the breadth or the width or the height. The letter itself doesn't matter as long as the concept is there. A lot of textbooks use h for height, which I must admit I don't particularly like, because I think of height as vertical rather than horizontal. Now I'll leave b minus a here. What I used to do with my classes, once they understood this, is I'd challenge them to make up their own rule. Each student in the class would be asked, given these 3 function values, this is Simpson's rule, and we might have, my name's Graham, so we might have Graham's rule. And I would say the area would be approximately b minus a. We can't change the width of this double strip here, but I might have 2 lots of y0 and 5 lots of y1 and 3 lots of y2. Just because I felt like it today. What would I divide by to make it an average length? Well, 2 plus 5 is 7, plus 3 is 10. And students around the classroom would do this. One might choose 3 of these and 8 of these and 1 of these, or 2 of these and 11 of these and 7 of these. I really didn't mind, as long as this number totaled the number of lengths on the top. So it's the average length times the width or the breadth. And then we would calculate based on the values. For example, here, if I just remove these, I'll use black. Oh, the black's gone. I'll use blue. If this was worth 5, and this was worth 8, and this was worth 11, actually they're going up by 3, so let's change that. Let's make it 14. We would substitute 5, 8 and 14 in here, here and here, or here, here and here, or here, here and here. And every student around the classroom would substitute those values and we would compare the results. And interestingly, they would cluster. Not very far away from Simpsons Rule, or the trapezoidal rule, which we do as well, or, because we would often do it with a function we knew, we would calculate the exact area using calculus, and we would find they would all be clustered fairly close together. Now, I've got no justification for that. I've got no rationale. Simpson and Johannes Kepler had a rationale for this, and that was they tried to approximate a parabola through these 3 points, which made perfect sense. So this is actually a very lovely little system, and I hope that's demystified this demystified Simpsons Rule for you. So let's draw a graph. I'll use the same graph I used for the trapezoidal rule last time, and we'll analyse it using Simpsons Rule. I'm not sure which notation I'll use yet. I'll just erase this and then use one of them. So let's have a look. Now, when I was demonstrating the use of the trapezoidal rule, I used this function, y equals x squared plus 1. I've decided to use the y notation. And here we are with the 2 strips, which we could use as 2 separate instances of the trapezoidal rule, or one instance of the use of Simpsons Rule, because Simpsons Rule uses a double strip. We need 3 values for Simpsons Rule. Let's write Simpsons Rule out. It's approximately, I'll write it the more conventional way, b minus a over 6. Sorry, I was going to use y notation, not function notation. Y naught plus 4 lots of y1 plus y2. And to find this area, we would say b minus a, 3 minus 1 over 6. I do prefer the 6 underneath, and I'll show you that later. The first y value will be what we get when we substitute 1 in the formula. 1 squared plus 1 is 2. I'll write the value on here. When I substitute 2, I get 2 squared is 4 plus 1 is 5. And substitute 3, 3 squared plus 1 is 10. So I'm going to get 2 plus 4 lots of the number in the middle, this value, the function value there, and the function value on the end. 3 minus 2, 3 minus 1 is 2. Sorry, I was thinking of the answer first. 4 5s is 20, 30, 32. Now, 2 divides into 6 3 times, and 3's into 32 makes 10 2/3 units squared. The way I would have written it, if I was teaching a student who was struggling, is I would have said this. It's length 1 plus 4 times length 2 plus length 3 divided by 6. That is the average length times the breadth. If you've looked at my other videos, you'll realise that I'm constantly referring areas back to length times breadth, the area of a rectangle. And there's my average length. So I like the 6 underneath these function values. And I won't go through it all. I will write the next line. We would have written these same values, 2 plus 4 lots of 5 plus 10, all over 6. And the breadth was 2 units. And you can see that this and this, or these two lines are the same thing. We have the 2 out the front, the 6 on the bottom, and these values in the middle. We get exactly the same value. It's just written slightly differently. One last thing before we go. What happens with multiple uses of Simpsons Rule? What if we were asked to go and add another 2 strips at 4 and 5 to make another use of Simpsons Rule? Now obviously I can't get right up to the parabola up here. Well, the function value at 4 would be 4 squared plus 1 is 17. The function value at 5 will be 5 squared plus 1 is 25 plus 1 is 26. How would that be shown with these formulae? With my formula, with students who struggle, I would just say write the same formula out again. L1 plus 4, L2 plus L3 over 6 times your breadth. And that is our average length times breadth. Now, to distinguish between the two, we could call this number 1 and this number 2. Or another way of writing it would be to put a bar down here with the 1 and a bar down here with the 2. That's another notation could be used. It's just a way of saying that this is a different set of conditions or different numbers from these ones. What about the y notation? Well, I'll do it in blue. It would still be the same width, over 6 rather, even though this b and a are different. 5 minus 3 gives 2, same as 3 minus 2, 1 gives 2. So we can still use b minus a, it'll give the same value. And what are the 3 function values here? Well, if this was y0, and this was y1 and y2, this one here is going to be y3, and this one's going to be y4. Just counting along the ordinates. So, to deal with this double strip, we're going to use y2, y3 and y4. So it's going to be y2 and 4 lots of y3 plus y4. Sorry, the 6 is out here. I've got to get used to the fact that books do it differently. When you combine these, I hope you realise we have y0, we have 4 lots of y1, because the y1 is in the middle of this double strip. We have 4 lots of y3 because it's in the middle of the next double strip. And if we had another one over here, we'd go y4, y5, so we'd have lots of y5. You notice these are odd. 4 lots of y1, 4 lots of y3, 4 lots of y5. All the odd ones we would have 4, we'd count 4 times. Notice that y2 appears in this formula at the end, and it appears first in this one because it's on the boundary. So it's counted twice. It's counted once in this use of Simpsons Rule and once in this. So Simpsons Rule, when it's written out in full using y notation, would be that the area is approximately height on 6, I'll ys the word height for this width of the double strip, times y0 plus yn for the last y value if you've got a great number of them, and they're going to be 4 times the odd ones, the y1, the y3 and so on, and 2 times the even ones, even function values. And you'll often see it written in this form in books. The notation to explain the odds and evens, and certainly to do it with function notation, is more fiddly, and I really don't want to go there at this point. If you are expecting to do mathematics at university level, then you really should learn the more appropriate terminology. But for a lot of school use, this is quite sufficient. And certainly for students who are struggling, I just encourage them to write out this area formula as many times as is needed. So there is Simpson's Rule in its very simple format. It's the breadth times the average length, or average length times breadth, where the average is 1 and 4, and 1 is 6 lengths divided by 6. A little unusual. But there it is. Please write comments at the bottom of this video if this has in any way helped you, or if you have some constructive criticism. I'd appreciate that you like the video, and I certainly would love you to subscribe to my channel to find out about future videos. Thank you again for watching.